we've talked about various different types of engines. We've talked about marine propulsion and how it affects engine load profiles. Now we've talked about aviation propulsion, aviation engines, fuel economy, and internal engine stress based on air-fuel ratio changes. So at the end of the last video, or the first video, we'd been talking about this particular graph. This graph shows the bottom two curves are the hull prop demand curves, and displacement speeds on the left from 7 miles an hour up to about 11 miles an hour, and then planing speeds on the right from 13.5 miles an hour up to about 21.2 miles an hour. And it shows how much horsepower the hull is going to pull at those various speeds. And then we have the engine wide open throttle lug horsepower curve. And then right below that, we have that same engine lug horsepower, but at reduced air-fuel ratio, or leaner air-fuel ratio, showing a slightly lesser amount of power. So we want part throttle engine performance analysis. That's what we're trying to do here. In the late 1990s, a young mechanic that I work with named Charles Hollis talked to me about desktop dynos. He owned a Camaro and he raced his Camaro, and he built the engine in it, and he used a desktop dyno to determine what cam to put in it. He actually specified the cam that he was going to use and had it built to put in his car. So I bought this book and I read it, and I started experimenting with desktop dynos in the late 1990s. Back then, I eventually purchased Engine Analyzer from Performance Trends. This is the main screen for Performance Trends Engine Analyzer. You can see that it has a short block subroutine, a head spec, intake system specs, exhaust system specs, cam and valve train specs, turbocharging specs. I'm running naturally aspirated, so I'm not really using that. And then there's a calculate performance window. Here's the short block specifications for my 383 crate engine. I programmed it in based on the engine that I bought, and I'm trying to duplicate that engine as precisely as I can. These are the cylinder head specifications. This actually came down from a drop-down menu. The actual cylinder head used on my engine was already programmed into the computer, so all I had to do was pull it down. Here is the intake menu for the Performance Trends Engine Analyzer. Now, I've decided to use a dual plane manifold and a carburetor. And this program lets you change the CFM rating, and that's how you simulate part throttle operation. Now, industrial engines are not rated at wide open throttle. They're rated at some number below wide open throttle. And the reason is, when you sell a customer an engine that's supposed to develop 100 horsepower, it's got to develop 101 horsepower in order to prove that it's right. And it has to do so time and time again for the entire life of the engine. So I've decided, even though I put a 600 CFM carburetor on it, that I did all of my testing at 500 CFM for wide open throttle, but not for part throttle. Here is the exhaust menu. I am trying to duplicate what I've got on there, but it doesn't matter because I decided to put in full exhaust. You can change the CFM rating on the full exhaust to get the back pressure you're looking for. Marine engines exhaust below the waterline, so they all have back pressure all the time. Now, this program is not really set up to do that, but within a limited RPM range, you can change the CFM rating on the exhaust to get the back pressure that you need. I spent a lot of time on the cam menu and doing a lot of test runs with different cam configurations. If you look down here in the comments over here, you'll see that I've got the lobe numbers from CompCam right there, and I've got the timing numbers, all of the stuff that came from the CompCam's catalog. What I could has been programmed in here to try to match exactly everything that I'm doing. Now, you can see in there that it shows lift for rating for timing events, and it is set at 50 thousandths of an inch. I don't particularly care for that. I prefer seat-to-seat timing and everything, but I know that you guys compare cams based on that. If you look in the comments, you'll see that I've got duration at 3,000, duration at 50,000, duration at 200,000, and that's because part of the program required those inputs. And I'm really more interested in seat-to-seat timing than I am in 50 thousandths lift timing. Doesn't mean much to me. Here's the menu that I used for calculating performance for the overall power curve of the engine, the lug curve. And you can see that it's starting RPM 1600. I did 15 steps, 200 RPM for each step, and that gives me an overall view of what the engine is supposed to do. Here's a sample of the basic output of this engine at wide open throttle with a 500 CFM carburetor. Notice that I've got a half PSI of exhaust back pressure, third line across, at 4,000 RPM. And at 4,000 RPM, I'm looking at 412 foot-pounds of torque and 313.8 horsepower. If you go to 2,000 RPM, you'll see that I've got 383 foot-pounds of torque and 146 horsepower. And the brake-specific fuel consumption is sitting around 416, 0.416. 0.416 is the same brake-specific fuel consumption that a D399 gets. So that is very similar to diesel engine performance from a gasoline engine. When you run a engine analyzer, calculate performance tests, you also get special calculations. And some of the special calculations shown here are dynamic compression ratio, valve opening and closing events, both intake and exhaust. And I ended up using the exhaust valve opening compared to the intake valve closing events to calculate dynamic expansion ratio. So I have a 16% increase in dynamic expansion to try to get more fuel economy out of my engine. Here are the special calculations that were provided for the cam that was originally supplied with the engine in my crate engine. The dynamic compression ratio has been adjusted with timing to get to the same dynamic compression ratio that I have, 7.53 versus 7.54, about as close as I can get it. But notice that the dynamic expansion ratio is the same. In this case, the dynamic expansion ratio is the same, whereas on the other unit, it was 16% more expansion than compression. Here is the overall dyno test, same parameters for the as-supplied cam. And notice at 2,000 RPM, the brake-specific fuel consumption went up to 0.420. It actually went down at rated speed at 4,000. It went down a little bit, but I'm not going to be running up there very often, so it doesn't matter. If you look again at what RPMs and horsepowers I'm going to be running and for how long, I've got 0% at 255 horsepower. I've got 0% at 180 horsepower and 2% at 120. So below 180 horsepower is really where I want to analyze this machine. I'm going to run 78% of my time at 15 horsepower. I really want it to be efficient at 15 horsepower. So here is a 165 horsepower V8 operation, rich of peak. So there's a discrepancy in the brake-specific fuel consumption. So we've got our fuel consumption at 78.25 gallons per hour. It's rich of peak. We're not changing that. It's supposed to be 12.5 to 1 air-fuel ratio. The computer tells me that it's 0.459 brake-specific fuel consumption. But when I calculate it, it comes up to 0.47427. And I'm going to assume that the fuel consumption is right and the BSFC is a little bit off. So that's how I'm going to do the rest of the thing. So based on that, I've got 12.65 horsepower per gallon, and I've got a range of 188.35. Here we have a lean to peak operation for 165 horsepower. Now, in order to get lean to peak, you have to actually make more horsepower than you need, and then you multiply it by 0.92 because you lose 8%. So you take 179.35 times 0.92 is 165 horsepower while it's running lean. You do the same thing with the fuel consumption. You take the fuel consumption of 83.54 multiplied by 0.75. That gives you pounds per hour at 62.655. You divide that by 6 and you get gallons per hour at 10.4425. You use that to calculate based on the output horsepower. You use that to calculate your brake-specific fuel consumption. That gives you 37.973 BSFC. That's as good as a diesel gets. And then your horsepower per gallon is 15.801. And that's comparable with some of the diesels we saw in the Nebraska tractor tests. Calculated speed is 20.47 knots, and 120 nautical mile range is 120 gallon nautical mile range is 235.23. Here we're doing 150 horsepower, rich of peak, and we've got a 12.537 horsepower per gallon, and we've got 195.77 120 gallon nautical mile range. Here again, 150 horsepower at 2873 RPM. We're running lean of peak, so we multiply the horsepower down by 0.92. We multiply the fuel consumption down by 0.75, and that gives us 57.3525 pounds and 9.5588 gallons per hour. BSFC is 0.38238, which is comparable to a diesel, and horsepower per gallon is 15.69 horsepower per gallon. The range now gone up to 245 nautical miles. Here is 135 horsepower. I've got Richard Peak on the right with 203 mile range and 12.377 horsepower per gallon. And Lena Peak, I've got 15.54 horsepower per gallon and 255 nautical mile range. So I'm up by 25% on my range. Here we have 120 horsepower, 2667. This is lean on the left and Richard Peak on the right. Our range is up to 267 compared to 213 Richard Peak, and horsepower per gallon is 15.29 compared to 12.203 Richard Peak. So you can see that there's a clear advantage going Richard Peak. Going lean of peak. This is the spreadsheet that I created to determine hull performance. The very top set of columns, that is planing speed from 165 horsepower up to 300 horsepower. And then the center set of columns, center set of lines is from 165 horsepower down to 60 horsepower. These upper two sets are planing speed, and then the bottom set is displacement speed. And I use formulas from Dave Gear's Propeller Handbook to generate all of this information, and then I tried to duplicate all my performance in the engine analyzer so I could have correct information for data on my engine performance. Here I've combined all the data into a red fin fuel and air curve. So you can see the red fin right off. I've got the MR numbers across the top, and then I've got another set of MR numbers handwritten that line up with specific curves on the graph. so it's easy to figure out which MR number goes with which curve. I've got horizontal lines drawn, the three there together, that is the peak power band. And if you notice, the green lines of constant airflow are vertical inside the peak power band. When you go down lean to peak below the red fin, the fuel consumption in gallons per hour curves, those are vertical in the lean to peak operation. So this graph has been expanded to cover from 0 power on the right all the way over to 85% on the left. The left is 255 horsepower, and the smallest horsepower that I have data for is 7.54. I've basically got all the horsepowers lined up at 15 horsepower intervals, and I have an engine analyzer sheet to go with every set of data. Here is the power graph or the power analysis for 90 horsepower, lean to peak on the left and rich to peak on the right. This happens to be the highest planing range of all of the ones that I analyzed. So this shows me a total range on 120 gallons of 301.52 nautical miles, lean to peak versus 225 nautical miles rich to peak. The horsepower per gallon is 14.9564. Now that is nearly 15, but not over it. But this is the best range while you're on planing. Here we have analysis for 75 horsepower at 2280 RPM. Again, we're planing speed at 13.8 knots or 15.87 miles an hour. Notice that the range has dropped off a little bit to 298.58, whereas before it was 301, so we are taking a little bit more power to push the boat at the speed in order to get the fuel economy. So our fuel economy is suffering a little bit here, but not bad yet. Here's the analysis at 60 horsepower, and we're down to 277 on our range, and we're down to 11.225 on our fuel consumption. Notice that the vacuum is 12.6, and the exhaust back pressure is 0.4. So at this point, because we're going in lower RPM and because we've got a lot higher vacuum, we're running less fuel economy, and we're getting a shorter range because of it. So this is 30 horsepower comparison at 1367 RPM, rich a peak on the right and lean a peak to the left. This is the lean a peak strip. Multiply engine power by 0.92 because you lose a little bit of power, and then you multiply fuel consumption by 0.75 to give you lean a peak. So it's 3.3375 gallons per hour lean or 4.531 rich. Horsepower per gallon is 8.98 or 6.627. And range is 309 versus 228. So that's both rich a peak and lean a peak running on all 8 cylinders. Here is a rich a peak only comparison, and it's 8-cylinder engine versus 4-cylinder. Now, how do I run the 4 cylinders? What I do is I let one of the float bowls run empty. Once that float bowl is dry, it's running on 4 cylinders, and those 4 cylinders would be the outside on one side of the engine and the inside on the other side. Got even fire and order, and should run pretty smooth like that. To get the correct horsepower while you're running a 4-cylinder lean a peak, you got to do 2 things. You got to take the dyno tested horsepower, multiply by 0.92 to correct for lean a peak, And then, because you're running 4 cylinders instead of 8, you have to subtract off the motoring horsepower of the other 4 cylinders. So to do this, I tell it's a short block, it's a 4-cylinder short block, and then I add back in the power loss, or subtract the power loss from the from the extra 4 cylinders. So I've got it up there, it says 0.92 minus motoring horsepower. That gives me my 30 horsepower there. And then I take the fuel consumption times 0.75, because it's only burning fuel on 4 cylinders, and that would be right for the computer simulation. Now here's 4-cylinder Lena Peak on the right versus 8-cylinder Lena Peak on the left. So we just did the 4-cylinder Lena Peak numbers. Now we're doing the 8-cylinder Lena Peak numbers. Notice we're running all 8 cylinders. And so look at the difference in fuel economy. Horsepower per gallon, 8.986 on the 8-cylinder engine and 13.8935 on the 4-cylinder. And then the range, 309.9 for the 8-cylinder or 478.9 for the 4-cylinder. There's a clear advantage to turning 4 cylinders off at light load. So let's say you're running along on 4 cylinders, and in this case this is Richard Peak, and we know that we'd be putting out 30 horsepower. What would happen if you turned on the other float bolt and you didn't touch anything, you didn't reduce the throttle setting or whatever? You'd go from 30 horsepower to 72.6 horsepower at the same RPM. Well, that of course is going to cause the boat to speed up, and the boat's going to speed up, and the horsepower draw is going to increase, the RPM is going to increase, everything's going to increase. So you're looking at more than doubling the power output by simply turning on the carburetor, so that you're running on both float bowls instead of one. So this concludes part 3 of this discussion. I'm almost finished. We've got to go through 15 horsepower comparisons and then put it all back together for a final recap of what we've done. But I hope you guys have learned something, and I hope you found that this presentation was enjoyable. I know it's a little long and it's a little bit dry, but for you guys that are into this kind of stuff, it should be pretty good. Talk to you later.